So this is the preliminary quiz. Go to lab experiments, and that's one of the first. I know there are too many syllabi posted on my site, my point of view. Very important guidelines. Preliminary lab quiz. I know it says about 20 to 40 minutes, and I'm gonna try to really rush through this one. Okay, so open it, begin, and I intend to just give the answers away. So all of these that you see here labeled following statements regarding the lab guidelines ought to be true. So you can just click true, 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 true. This one here is kind of like a filler question. This one is in a backward order if you carefully check that. I do that sometimes if the answers are short. This one here, when the answers are long, actually, I'd like to go in straight across here. So this one is about random and systematic errors for distance, time, and mass. And so you can carefully read through these here. This one here, also longer answers, so I do have them in the correct order here. So you will encounter measurement and, well, hopefully not equipment errors, but they're part of an experiment. Well, we try to get rid of equipment errors, but that could be something like friction here, measurement errors. That's actually when you go back to this one here, you will have some kind of random errors. The others, when you carefully read through these here, you ought not to have calculations or rounding errors. Okay, get rid of calculation errors, do the computations correctly, and round correctly. So that shouldn't be there. There is no such thing as human error. Yes, all measurements are taken by humans, but you have to specify what measurements instruments are you actually using. So therefore, do not mention human error. All right, significant figures. You might have already noticed that I hit you over the head with that. So when you do these here, for example, I'm gonna try to grab the calculator. The first one here, 137 grams divided by 28 milliliters or cubic centimeters, rounds to 4.9 grams per cubic centimeters. Two significant figures because of the 28, which has two. The other one, when you go through this one here, you will see that it actually boils down to 4.9, 49.11, so 49.11 divided by 20, 2.4555, and rounded to 2.456 seconds. Notice that the 150 centimeters here doesn't play part in that, and the 20 is an exact number. Exact number also doesn't take part into significant figures. This one here is simply 9 times 1, 9.00 times 1.00, which is still 9. That's what your calculator shows you. However, the correct answer is this one here, so 9.00 joules, because this was measured accurately to 3 significant figures, hence 3. And let's see the last one here. It says multiply the exact number 2 with gravity, 982, and with the height of 53. The 53 gives it away. That's 2 sig fig. That's what we ought to round to. And then we're supposed to take the square root because it says so. Take the square root of that number. There we go. And we come up with 322.63. And because of the 53 here, the 2, again, is an exact number. So the 53 is actually the one with the least sig fig. So this one here rounds to 320, which is 2 sig fig, the 0 here just being a placeholder. So there we go. All right. Here, this one, they're all true, except the last two. They're false because I said so before. Unspecified human errors, no, don't write them in the conclusion. No computation or rounding errors allowed. So it's the others that you come across. that you ought to list in the conclusion. The conclusion usually boils down to results or examples of the results, comparing them, commenting on them. And then an error analysis where you have to say, hey, these were the measurement instruments that we used. All right, the next one here is just a filler question. So this one is 2 and 4 and 4, and the rest is 2. There we go. And this one here goes straight across. So A, B, C, and so on. And notice that there's some experiments that are more accurate than others, such as the density. There are no moving parts. You ought to be able to come within 1% of the required result, because all you do is caliper and electronic scale. Acceleration due to gravity, yes, the pendulum is swinging, but it's swinging slowly and at a very constant rate, very smoothly. Again, very high accuracy. You ought to come out with something really close to 982 centimeters per second squared. If you come up with 1020, that's too far off. You ought to be between 975 and 990. Torque and center of mass is also very accurate because all you really use is the electronic scale and a ruler, and you ought to come up with the correct center of mass for this one. And again, this one here goes on alphabetically. This is all in the correct order already. There's another one here, DC circuits. That should be second to the last one, which is also Ohm's law. Again, you're just using the ammeter, the ohm meter, the voltmeter, so the multimeter overall, and you ought to come up with really accurate results. The last one, in fact, too, capacitance is also very accurate. There's some experiments that are less accurate, like, let's see, especially the centripetal force, 20%. Yeah, and that's about it. Where'd it go here? Oh, projectile motion and ballistic pendulum could be even more than 20%. And the heat flows as well. That's even an underestimate of this one here. We usually get relatively large errors on this one. All right, again, this is all alphabetical. And then here, this would be, if you look here, then you can, oh, it's this little video here, I guess. So R2D2, and I think he has these here, and he helps out with the DC circuits and heat engines. And that is the preliminary lab quiz. There we go. All right, the next one is pre-lab 1. So let's see, lab experiments again. Scroll down to unit 1, metric system, and click on pre-lab. And here we go. So here, as you attend the lab intensive, you just copy this one here and say, all right, I, the student, and so on. Of course, here you just put your name, will attend lab intensive. Forget about this one here, lab intensive. So let's see. Again, I'm just going to give the answers away. So these first two are correct objectives for the measuring and metric system. These are already in the correct order. So if you look carefully at these here, then you can see that they nicely go across estimates. For example, it is important to assess the validity of a result, make an estimate before if you can. Or the first one, physical quantity, number, and unit, all three must be written either separated with an equal sign or tabular form. So for example, velocity equals 55 miles per hour. There you have it. Physical quantity, number, and unit. By the way, these answers here, when you look at the lab manuals as they're posted within Blackboard and as Word documents, look for the blue stuff that's in there. So you have to actually look at them at the electronic versions to see that, oh, they actually give these answers away. All right, let's go ahead here. So these are actually in the reverse order. And if you carefully look at these, Then you have the last one. Yes, in order to get from kilometers to miles, either 1.6 or divide by 1.609 or multiply. Depends on which direction you're going, depending on the desired accuracy. Or the last one, 2.2, or 2.205, depending on the accuracy, kilograms to pound mass. This one here, I want to say all of these are correct. So this is about significant figures again. So pay attention to them. It also says in here, once in a while, if you have one too many or one too few, don't worry about it. But it shouldn't be the 8 from the graph, from the calculator. So don't do that. So let's see, there are experimental errors here. So set up correctly as renders any measurements meaningless. So try to avoid experimental errors. This one here still. And then systematic errors are the next 3. So for example, you're set up an incline that's supposed to be at 30 degrees, but you set it up to 35 degrees and you keep doing that. Well, that's in systematic error. Try to avoid that. So let's see, how many did I say? The next 3. Yeah, occasionally few such errors, systematic errors, you can't get rid of them. The friction of a moving object, you cannot be able to get rid of the friction, so it's going to be in there. Or the reaction time that you have when you're using a stopwatch or your cell phone as a stopwatch. You have that 0.1 seconds in there. Can't get rid of it. Each measurement, so this one is then random errors here, so each measurement contains a measurement error that is restricted to the accuracy. And this error cannot be avoided, can only be minimized. All right, the next one, these are all correct here. So for estimates, important to have a good idea of how large something may be before actually measuring it. So if you measure a room to have a length of 55 meters, which is 160 feet, there's probably something wrong, if you measure a regular classroom that size, unless you have a huge classroom, which we don't have here. So the last one, by the way, is false. No, that's not what the point is of an estimate. The estimate is supposed to give you a good idea of what you're supposed to measure, but it doesn't have to match measurements exactly. All right, I want to say that these are, so when you look carefully at Lab 1 manual for metric system, you can find these one here, and they should be in the correct order here. I'm going to take a little break, and I'm just going to show you well, actually, I don't think I have to take a little break. It's right here. I want to just show you the pendulum lab, for example. Okay, it went somewhere. You can download it. So it'll take a little moment here. There we go. There we go, maybe. There we go. Okay, there we go. Okay, remember what I said about the blue stuff. So there it is. So look out for the blue stuff in lab menu, not the links here, but the blue stuff here, which are the answer to the pre-lab questions. All right, that's what I want to point out. All right, let's see our pre-lab 1. So objectives for the pendulum, the first 3, if you read carefully through this. The theory for the pendulum, they go straight across. Newton's second law plays in here. And when we solve for it, we come up with G for the acceleration due to gravity. It's the objective of the pendulum, which is what it says here. We're in Alaska, so we have to come up with something really close to 982 centimeters per second squared. And this is, because it's very accurate, this is what you should come up with in that range. All right, I want to say that all of these answers here in this question are in the correct order already. So there we go. And so on. I don't see any exception to that. So yes, they're all in the correct order. The example here, you would have to either look at a video or careful in the lab manual to actually see that the first 4 are correct. The other statements might be correct too. Something like that. I forgot, but in any case, they're not part of the video that I point out here or the lab manual itself. You should come across these numbers. Notice also that I came up with pretty good results, 976, 981.3, 977.4. You ought to do just as well because this is a really accurate experiment. All right, that was, oops, this meant to be clicked. So that's pre-lab 1. All right, so pre-lab 2 and lab experiments, unit 2. And there we go. Lab 2, same thing as before. I had a student participate in the lab intensive. First one is about the force table. Click the last 3, I believe. Yes, correct. Here, there's only one question, and the first answer here is correct. And then on the next one, these are all in the correct order. So there we go. A, B, C, D, E, F, G. It's all good. The next one, the first 4 are correct. Notice the different colors. What happened here is that in the lab manual, I put a certain example in here, and in my video, I put a different example. I don't know how that happened. It was a long time ago. But anyway, that's why you see 2 statements here for each correct answer. Let's see here, make up a vector problem. I'll let you do that for forces. So you have to look at those chapters in the book, online, see, oh, what is that actually here? Some kind of vector problem that involves a real situation where you add vectors, force vectors. Right, density objectives. It's the last 4 that we're going to cover. This one is the correct order already. So if you look again carefully for the blue stuff in the lab manual, you will find these here. And the next one actually skips. Notice there are 8 possible answers, and this one skips every other. So this is like A, C, E, as I said, almost skips every one. So F, there we go. All right. These days, it seems like that we're using specimens that are actually round. So you have to measure the diameter and come up with actually spherical shaped specimens. So spheres, that's the volume for sphere, right? I've seen it in geometry or algebra. The next one should be all in the correct order here. Again, this is a very accurate experiment, so I should point it out in here that you ought to come up with very, very good results. So for the density of aluminum, which is 2.70, if you come up with grams per cubic centimeters, if you come up with 2.73, you're right on. If you come up with 3.1, no, that would be 10% off, and no, it's way more accurate. And I think that was actually the last one here. So I'm going to stop this recording here. Pre-labs 1 and 2 and the preliminary lab quiz. That's enough for now.